So last time, what we talked about was this right here. So we mentioned this very briefly at the very end, but what we talked about beforehand was this, which is in front of us right now, which is the phase change that goes on during the liquid to or liquid to vapor change. And then we also talked about PV diagrams, things like this right here, what they look like. So this graph. And we also talked about fixing the state. And so fixing the state, as I said last time, so fixing the state was essentially getting two separate intensive properties to find everything else about the state. If we know everything about, if we find two things that are, separate intensive properties about what is happening in one state, we can find everything else. We can find all the other intensive properties as well. So that's what it means there. So essentially, like let's say if I gave you two things, if you found two things about the state right here attached to this line, you can find everything else. Like if I gave you pressure and let's say quality of 0, you can find everything else. You can find temperature, internal energy, volume, all these other things. You can find it all. And we will be doing just that today as well. So as we move back down to where we were. And then last time I mentioned the phase change. So on the far left side of the chart, like the PV diagram with the saturation curve in the middle, the far left side, outside of the saturation curve, is the subcooled liquid region or the compressed region, interchangeable terms. Inside of the saturation curve is the saturated area. So that means that it is some percentage of liquid and vapor, right? Phase change is happening. It's going from one to the other one, right? Either from vapor to liquid or from liquid to vapor. And then at the very far right, outside of the region, is the superheated vapor region. All right. And then this right here, this was a new property, or a new intensive property, I guess we could say, which is X, which is quality. So let me pull up EpicPen. So this is a new intensive property that we found last time. And remember what this is? This property right here is essentially the percentage of vapor there is inside of the saturated curve. So, if we're, inside of this region, right? And we know that it is saturated. It's somewhere under this umbrella, right? Somewhere in the saturated region. This right here, this quantity, X, tells us how far we are in. So like I said last time, if you find that there's 7 kilograms, or let's say there's 10 kilograms total, 7 kilograms of vapor, and obviously mass and liquid together gets you 10, you know this is now a 70% vapor, right? Which would be somewhere over here in that region. But that on that line, essentially that 70% thing doesn't really matter, except in which, so you're going to multiply in. It's essentially a multiplier that helps you find other properties, because as you'll see in a second when we start talking more about the tables, it does not list values of, let's say internal energy, U, for every quality of vapor, right? It lists it for X equals 0 or 1. It does not list it for anywhere in between. And so that's what this is essentially. That X quantity is you take the difference between those other two, like the X of 1 and 0, and that X quantity gets you a percentage in between. So that's that's the point of finding that. All right. And then we start today. So starting today, like I said, this is a very important lecture. And this is because this lecture is the basis for essentially all other ones that come in further classes. So that'd be 400, ME 400, and a lot of what's left in this class. Pardon me. So essentially what it is that retrieving thermodynamic properties, and how we do them in this class is you do them by use of tables. And I showed you last time, but this is what the table looked like, and I have posted them in this Discord, so you should all have these tables up right now. Open them up, and we're going to be looking through these tables as I go through it. I want you guys to try and follow along, just so you understand what I'm doing. But this is what they look like. And as you can see at the top, just to introduce it, it shows you what liquid or what fluid we're working with. This is water. But as you move down, like if we continue on, you'll find that this right here is refrigerant 22. There's R134A. There's ammonia. I think propane, maybe. There's a lot of them, but essentially the ones that you're going to be working with are mostly water and refrigerants. So, or water in like R134, R12, R22, and ammonia very, very, seldomly. But this is what they look like. Alright, so let's get back here. So, it says, thermodynamic property data can be retrieved in various ways, including tables, graphs, equations, and computer software. This is all true. Engineering equation solver can solve all of these without using any tables. That's because the tables are sort of programmed into it, and they can tell you if you give them two properties, they'll spit you out all the rest of it. And it says, the emphasis of 3.5 and 3.6 is to follow, and 3.6 to follow, is on the use of tables and thermodynamic properties, which are commonly available for pure, simple, compressible substances of engineering interest. The use of these tables is an important skill. The ability to locate states on property diagrams is an important related skill. This right here, I'm not worried about. And it says, skillful use of tables and property diagrams is a prerequisite for the use of the software. So what that basically means is that, for engineering equation solver and other things like it, you have to already know what you're talking about, right? Like, for example, if you use like AutoCAD or something, or let's say Autodesk or SolidWorks, you can build something, right? Like any one of us can build something in SolidWorks, but will it actually work in practice? Well, that takes experience and that takes knowledge of the properties at hand, right? Any one of us can go, yep, that looks like a bridge, let's make it, but we don't know if it actually works. You have to have some understanding beforehand. The same thing goes with this. If you don't know the thermodynamic properties very well and how to find them, it won't help you very much to use a program, because you have to know what you're doing beforehand. All right, and so with that, it says, since tables for different substances are frequently set up in the same general format, the present discussion centers mainly on tables A2 through A6, giving the properties of water. These are commonly referred to as the steam tables. So when I say something like the steam tables, that's what I mean. I mean the water tables, essentially. Tables A7 through A9 are for refrigerant 22, A10 through 12 is 134A, A13 through A15 is ammonia, and tables A16 through 18 for propane. But yes, you can just see at the very top, right? So as I go back here, you can just see which one you're working with right here. It says saturated liquid or water, liquid vapor pressure table. All right. And then it says the substances for which tabulated data are provided in the book have been selected because of their importance in current practice. Still, they are merely representative of a wide range of industrial important substances. To meet changing requirements and address special needs, new substances are frequently introduced while others become obsolete. So what that means is that with every edition of the book and with every new edition of software, new things are added and fluids that aren't used anymore are taken out, right? Because there are some things we just don't use anymore because they were hazardous to the environment, toxic for human, to be around people. So we just don't use them anymore. All right, and now we're at 3.5. So evaluating pressure, specific volume, and temperature. So vapor and liquid tables. So it says the properties of water vapor are listed in tables A4 and of liquid water in tables A5. These are often referred to as the superheated vapor tables and compressed liquid tables, respectively. So let me go to those. So Compressed liquid tables. Let me see. So right here is the superheated water tables in A4, right? And so what this one means is that right here, it shows you all of temperature, specific volume, internal energy, enthalpy, and entropy at the top here. And it shows you the temperatures that they can range in, right? So for example, right here, pressure of 5 bar, the saturation temperature is 151.86. So right here is where it first becomes superheated, like essentially that's the saturation temperature. And that's what this sat number is right here, is it corresponds to that right there. All right. And so essentially they go by pressure. So as you can see, they kind of jump, right? You have 5 bar, 7 bar, 10, 5, 20, 30. They jump around a bit. Let me see if I can find those other ones. So right here, these are the compressed liquid water tables. So this is the for the subcooled region. Now, really quickly, we do not use these tables very much. And the reason being is because we approximate our values using liquid instead of the liquid water or the compressed liquid water tables. And the reason is because as they get more compressed, like higher pressures, things don't generally change all that. Like for example, the volume doesn't change very much. So things just don't. Basically, unless it's like super high pressure, we really don't change it. It's not interesting to us. And also, these tables kind of jump around, right? Like 25 bar to 50 bar is a huge gap. It's a huge jump, right? I mean, so essentially, your values, the chances of them falling directly on this are really low. And also, like I said, now we're doing 25, now we're doing 50 jumps. So I wouldn't worry too much about the compressed liquid tables. The ones that you'll be using the most are the superheated ones, the ones that I'm scrolling through now. And you'll be using the saturated tables a lot. So superheated and saturated are the ones that we'll talk about the most. And I mentioned that we approximate things in the compressed region. We will talk about that in just a second about how we do that as well. All right. So I talked about this right here. So it says, now let's do a for example here. It says, for example, in tables A4 and A5 at a pressure of 10 megapascals, the saturation temperature is listed at 311.06. In tables A4E and A5E, the pressure is 500 psi and the saturation temperature is listed at 461. So essentially what they did was they told you two different, this is the pressure table in metric, and this is the English values, right? And so A5E and A5 is the one that's in metric, A5E is the English. So we're going to do this really quick. So it says, to gain more experience with tables A4 and A5, verify the following. Table A4 gives a specific volume of water vapor at 10 megapascals and 600 C as 0.03837. Okay? So remember this. We have 600 C and 10 megapascals. So let's go to table A4. So table A4, this is A3. Move down. A4 is superheated, and so it gave us 10 megapascals and 600 degrees Celsius. So what you would do is you find 10 megapascals. This is 0.1, 0.3, so we're going to have to scroll down a bit. 1.5, 3. This is 10 megapascals right here. So we finally reached it, 10 megapascals. And then you go down to, here's the temperature. And you go across all the way to the table of 100 bar, 10 megapascals, which is just this section. So essentially you have to kind of draw a line here in the middle. These are divided into their own separate tables. So this is the 80 bar one, 40, 60, 100, right? And so if you draw a line across from 600 and you look over here and you see this column, you will see that for specific volume, which is this right here, our little v value, our meters cubed over kilograms, it is 0.03837, which is what they said it was, right? So we have verified that that one is true. So does everybody see how that one sort of worked? All right, and then it says at 10 megapascals and 100 degrees C, table A5 gives the specific volume of liquid to be 1.0385 times 10 to the negative third. So this one is the compressed liquid tables, which, like I said, we're not going to use very often, but just to show you that it is there. If we go to, once again, 10 megapascals and 100 degrees, you go here. And now, the reason why it says times 10 to the negative third is because this value right here is actually times 10 to the negative third. So for metric units, for SI, you add 2 zeros to this. So I know that might be confusing. And the reason being is because on these tables, it's really hard to just put like a bunch of zeros. Like let's say it had to go 0, 0, 0, 1, 0. There's just not a lot of room. So essentially, just the way the units worked out. And so for metric for SI specific volumes, you add 2 zeros to the front of it. So it's actually, the real number is that 0.0010385. For SI or for English units, you do not have to do that. For English, it just shows up perfectly as it is. All right. So hopefully you guys are following along a little bit how that works. I won't do the English ones because the English ones, you do the exact same thing, except you're in English units now. All right. And it says, the states encountered when solving problems often do not fall exactly on the grid of values provided. Interpolation between adjacent table entries then becomes necessary. Care always must be exercised when interpolating table values. The tables provided in the appendix are extracted from more extensive tables that are set up so that linear interpolation, illustrated in the following example, can be used with acceptable accuracy. Linear interpolation is assumed to remain valid when using the abridged tables of the text for solved examples and end of chapter problems. So what that means is that if our number does not fall exactly on here, so like for example, if we go back up here to the superheated tables, let's say I gave you 1 bar, which would be this table right here. So 1 bar, and let's say 180 degrees Celsius. Well, as you can see, 180 is in between 200 and 160 here. So our number is somewhere in between those two. And so, now obviously because they are halfway in between, you guys can probably make a very good guess. Since 180 is halfway between 160 and 200, you can probably make a good guess about what it is. And that's essentially what linear interpolation is that essentially it's we're assuming that the relationship between 200 and 160 degrees Celsius is a linear relationship, so everything in between changes linearly. Now, obviously, that's not true, right? Because not many relationships are perfectly linear. So we're making an assumption here, and that assumption is good to use for this whole class. Linear interpolation is fine, and it is always acceptable to show values in the table. And so if anyone doesn't know linear interpolation, I actually will pull up the linear interpolation. So right here, linear interpolation formula. So it is this right here. So if you guys can see this on my screen, it is. So right here, these are the table values. So for example, if I gave you that 160, right? 160 degrees, and I gave you 200 degrees, that would be x1 and x3, right? And let's say we were trying to find specific volume. Y1 would be the specific volume corresponding to x1, which is 160. And then Y3, similarly, would be the specific volume corresponding to x3, 200. And then when you write it into this formula, you'll end up with Y3, which is the specific volume corresponding to our temperature of 180 degrees. And this is also programmable. I have it in my calculator, and it takes a lot of time off of the table. You don't have to write this out. If you guys can get a linear interpolation program, or you can find it somewhere online, you are more than welcome to do it. And how you would write it into your homework is that you would say, let's say T2 is 180, right? Like let's say that was, remember, it's our example. T2 is 180C. You would say like interpolated or int and then you would say like H or V is equal to whatever number you found, right? You don't have to write out your interpolation steps, but I need you to tell me that you did it, because if you don't say that you did it, I can't tell. Let's say you end up getting the answer wrong. I can't tell how you did it, and I thought maybe you just pulled it out, right? Just randomly, just pulled out a number. So please write that you interpolated. But I would put this into a calculator if I were you. I have it, and I don't know if I can post the program for mine, but it's really easy to put in a calculator. And there's probably a YouTube video online that'll tell you how to do it anyway, so. Alright. And so this is just a graphical representation of what happened. Like I said, essentially, they assumed that the change between step 1 to step 2 was linear, and so they found the part in between, right? That was it. Alright. So now we're going to do some example problems here to really nail this one home. So we're going to do we're going to determine the specific volume, V, and internal energy, U, of water at 40 psi and 500 degrees. So really quickly, let me go ahead and get Paint 3D open. So Paint 3D. I'm going to write these questions out, and I really want you guys to follow along here. Do not fall behind just because of tables, right? I really want you guys to really give this a go, because I'm telling you, I cannot stress this enough, that this class, if you don't know how to read the tables, it will be impossible. Alright, so this will be our first question in the top left, and I'm going to do it too while on the screen, so anyone who wants to watch the video later is more than welcome to. So, as I said, we have P1, so pressure 1, I'm just going to call it that, P1 is equal to 40 psi, and T1 is equal to 500 Fahrenheit. What we are trying to find is U, specific internal energy, and we are also trying to find V, specific volume. So that is the first question right here. And so with that, what we've been given here, so really quickly, we have been given two independent extensive properties right at the very beginning. We've been given 40 psi and 500 Fahrenheit. Now that doesn't mean that we can directly solve yet, because I know some people may not have like a really good idea of what is a superheated value. Like for example, once you get used to seeing these numbers, you'll be able to tell. Although you should always check. Maybe I should rephrase. You should always check to see where it is. So that's the first thing you should do. So step 1 here. I'm going to go ahead and write you guys some steps, so maybe this will be more helpful. So steps to solving properties. So step 1, you should always just open up the table. So open the table to the right, or open the table. Let's just do that. So open the table. So the very first step is that. So, as I said, what we will do is I'm going to go find the table. So hopefully you guys can see this still. So it is, we got it in English units. If you recall, it is 500 Fahrenheit, 40 psi. So that means we must go to the English table, which is when the back turns green, that means we're in the English tables. Or blue, sorry, blue. So we are now in the English tables, right? And it also said that, is it water? It is water. So it says determine the specific volume and internal energy of water. So, water. And this is the liquid vapor table. And now this leads us to the next one. So we've opened the correct table. Right? Step 2 is to figure out what phase the fluid is in. So what that means is that we need to figure out whether it is subcooled, saturated, or superheated, right? Essentially, where inside of, the saturation curve, right, this thing, is it over here? Is it in here? Or is it on the outside of it over there, right? So we have to figure out where it is. And now how we do that. So everyone's going to follow along here, hopefully. So really quickly, we were given 40 psi, right? So let's go to 40 psi. That was one of our values, if you guys recall. So 40 psi, 500. So we can scroll down here to 40 psi right here. So 40 psi is right there on that line. And right here next to it is the saturation temperature. So let's just do sat. So it's the saturation temperature. So what that means, as we talked about the other day, is that at 40 psi, this is the temperature it has to reach for it to start boiling. Right? So let me go ahead and draw this out for you. So really quickly, I'll put this on a PV diagram. So right here, let's just say, so right here is 40. I'm going to just draw 40 right here. So 40 is right here. And remember, temperature lines, constant temperature lines go up like this. So this is the way our chart looks currently. We are at 40 psi. And the temperature, guys, really quickly, right here, on this line. So once we get to here, on this point in between, right, this temperature right here, when you get to here, has to be 267.26. So this temperature right here is 267.26 Fahrenheit. Okay? So let's compare that really fast to ours. What is ours? Ours is 500, right? 500 Fahrenheit. So now let's go back. Where do you think our number is? Are we higher than that number? Is our temperature higher than the one required to turn saturated, to start boiling? Anybody out there? Way higher. We are, so you know what we are, guys? We are superheated. Essentially, that's what it means. Is that, really quick, we had to reach 267 for this thing to start boiling. But remember, the temperature doesn't change inside of this region. So what ended up happening is that we got to here, we reached the end of the vapor, right? Essentially, all the water boiled to vapor, and then it started climbing again. The temperature started rising. So we are long past this. So we are not inside of this region. Right? And you guys already solved the next one. Because if our temperature was less than 267, what would that mean? Let's say it was like 200. Where could we be then? Yep, we would be over here at the other x. We could be over here. So this is the importance of finding where we are located, okay? Because if you don't find where you're located, you will use the wrong table. And so we have now found that we are a superheated vapor. So what that means is that we must go to the superheated table, right? So superheated table, which is the next one over, I think, after this, which is right here. So let's go and find it. 40 psi, right here. 500 Fahrenheit. So, really quickly, the first one is always V. This one is U, H, and S. Entropy and enthalpy are the last two. So, if we go over here, 500, you will find that our specific volume is 14.16, and you will find that our internal energy is 1180.1. Those are the two values that we are looking for. So we did it, guys. Yay. That's it. So right there that was solving that one. And now, so really quickly, whenever you're not in the saturated region, the properties are pretty easy to find, right? When they're inside the saturated region, that's when you have to use quality, that other intensive property that I mentioned previously. So let me go back and go ahead and solve this then. So figure out what phase it is. Once you have found the phase, use the intensive properties given or if it is saturated, one sec, to find the values on the table, or find quality to another. Curve. So essentially what I'm writing here is that once you have found where it's at, you can very easily figure out the next step. So if you found that it's superheated, you already have everything you need here. 40 psi, 500 Fahrenheit. Easy. We just went right to the table and looked it up. And it would be the same thing if they would have given us pressure here. Let's say they gave us pressure and internal energy. You could have done the exact same thing. Now you would have had to interpolate, right? Because what are the chances that somebody gives you an internal energy that equals directly 1180.1, right? So it could have been somewhere on here. But essentially, given pressure and given something else, you can find all this other stuff. It'll work out, right? So that is, but if you're given something in the saturated region, that's when you have to find quality to do the next part, and that's why I wrote this last part. You must find quality, and we're about to do one that I believe has us find quality. But right here, this sort of steps that we just did is how you solve things outside of the saturated curve. It's the same every time. All right. So now let's head back. So we found the first one. All right. So now found the first one. Let's go do the second question. So the second one. And I just found that our answers are correct. Yay. Now we have lecture 5, problem 2. Determine the pressure, quality, and internal energy of water at a temperature of 150. So let's go ahead and write these things out. So the very first one. So what's going to have question 2 is over here. So question 2. It is given us here. It is said we are to find the pressure, quality, and internal energy of H2O at 150. So T1 is 150 C. So we are back to the Celsius here. And a specific volume of 0.1 meters cubed. So they have given us little v is 0.1 meters cubed per kilogram. Okay? And it says calculate quality from the given information, or given by the volume. So that's the key here. So we're gonna go over this really quickly. But what we were trying to find is P1 equals that, U1 equals that, and I think that was it. Pressure, quality, and internal energy, and X1. That. So that is our problem. So really quickly now. Hopefully you guys already know this part, but we have to go all the way back up to the water tables for SI units, which I'm probably almost there. Let me see. So so this is the saturated water right here. Okay? So let's go back up. We were given 150 Celsius and 0.1 meters cubed per kilogram as a specific volume. So now, really quickly, let's go look at the chart. So we were given a temperature, which means that we are going to go to the temperature table. It works the same way as the pressure table, so don't worry about that one. It works the exact same way, but although the relationship here is inverted, so we'll talk about that in a second. But specifically, we'll get our number right now. So our temperature was 150 C, so we must go down to 150 C. Which is right here. So right here, we're following the first steps again. The first step was open the correct table. The second step, figure out what phase your fluid is in. Now, obviously, since the question told us to find a quality, I think you guys probably understand that this is in the saturated region, right? If anything ever says find the quality, it means it's saturated. It's in the saturated region because there's no quality outside of that. All right, so we're at 150 C. And our volume here, they gave us as 0.1 meters cubed per kilogram, okay? So really quickly, here is our range. So if you look at this one right here, let's pull these out. We have to find some way to figure out where we're at. So we're going to use the volume. So really quickly, these are our two values. So remember, it's 0.00, right? Because we're at SI units. And remember, right here it says times 10 to the third. So this is saturated liquid times 10 to the third, okay? So 0.001 0.0905, right? So that is this right here. Now, less than V1, which is less than 0.3928. So what have I've just written here is I've written our greater than, less than. So essentially, if you look at our numbers at 150, we have 0.00100905. Our number is 0.1, right? Is 0.1 greater than 0.3928? Anybody? It is not. Is it less than this number right here? 0.00100905. It's greater than. So essentially it's greater than the lowest range, but higher or lower than the highest range of values here, which means that our value is right in the middle somewhere. It's somewhere in the middle, right? So this little equality shows true. So this is true. And if this right here is true for our value of volume or our value of whatever it is that we're looking for, if this holds true, it means that our fluid is in the saturated curve. So once again, with your PV diagram or TS diagram, it means that our value is somewhere along these hashed lines. We don't know where yet because we don't have equality, but it's somewhere in there. But the important thing is that we realized it's in there. Because once we've realized it's in there, it means we know we have to find equality. If you don't know it's in there, you can't possibly know to find equality, right? So that's the first step, is we had to figure out where it was. And now we do. We do know where it's at. So now that we have that, we can do the first step now. So the first step. And now this is an equation that you guys are going to have to hold on to really quickly, okay? So I want you guys to hold on to the following. So this is the equation for all, it works for all of these properties up here. V, U, F, and S. It works for all of them, and is essentially just a manipulation of, another equation, and I will provide you all equations that you need, but let's do this one really fast. So let's go to the paint. It'll be easier there. So, really quickly, this is a equation that it helps. It basically is equal to the quality. So if we do this, x is equal to v1 minus vf over vg minus vf. And now you guys might be wondering, well, wait a minute, what the hell is vf and vg? Now let's hold on before you guys freak out. They are simply these numbers up here. That's a VG. VG represents the volume of the gas. So it's a specific volume of the all vapor region, essentially. Once you get to the very end of this, so let me go back to the curve. When you get to the very end here, so right here, let's say that this is our line. When you get right on the border here, that is the specific volume. It is VG. So VG is right there. When it's likewise, when you are on the very other side, this is V sub F, which is, I think, V fluid or something. I don't know why they do that or how they came up with it. I just know that that's where they're located. So essentially, this represents the range of values, right? It's VG over VF, right? Or VG and VF. So if we go back to our equation, let's make some sense out of it. So let me get rid of this. So let's make some sense out of this. So can anybody tell me, like, why this makes sense? Like, why is this the equation to find out what percentage we are in here? Does anybody like, mathematically, can you, like, think about why this would be an equation we would use? I honestly could not have said that better. Essentially, if you look at this in terms of distances, So that's how I would see it. But yes, you are correct. Essentially, remember I mentioned this as the progress bar, the loading bar. So V1 we know is somewhere in here. So let's just go ahead and write V1 is here, right? Our volume is somewhere in between. This right here is VF. This over here is VG. If you do V1 minus VF, this is the distance here, right? It's some distance to get us back to VF. The total distance is here. So essentially what we're doing is our distance that we've traveled over the total distance. And you know what that represents? A percentage of how far we have traveled, right? So that is essentially the quality. The quality is how far we have moved from the far left side, the all liquid side, to the inside, which is the all vapor side. And he is absolutely correct. That is exactly what it is. And so, however you want to think about it in terms of distances, progress bar, whatever helps you, but essentially that is what we are looking at here. And so, x1 is equal to v1 minus vf over vg minus vf. And this works for all other ones as well. So you could say x1 is also equal to h1 minus hf over hg minus hf. You could say the same thing for internal energy. You could say this for entropy as well. It all works. This equation holds true for all of them. Just to make that clear, it'll all work. But let's focus on the volume one for now. Okay? So volume one for now. So let's go ahead and plug our values in here. So V1, which is, our value is what? It is 0.1 meters cubed, right? For V1. The VF value is, if we go back to the table, because I erased it, let's go down here to 150. It is 0.001095. So someone hold me to getting that one right. 0.001095 meters cubed per kilogram. Sorry, I forgot the kilograms part. But essentially, it does. Since we're dividing by the exact same thing, these units are going to cancel out because quality is a unitless thing. It's just a percentage, right? It's unitless. So, right here, let's do VG. So VG, if you recall, I think it was 0.3923. And I'll go make sure of that in a second. Minus the exact same thing at the top, which is 0.001095. Right? So let me go make sure of that before I continue on here. 0.3928. I blame you guys for not telling me that was wrong. So, 0.3928. So, if you do this really quickly on a calculator, which... Calculator... Let's go ahead and do this. So 0.1 minus 0.001095. You get that. And then if you divide by 0.3928 minus... Okay, it's going to mess up because obviously I don't have parentheses on this. Is there any way to make this a different one that has parentheses? Anybody know? Oh, scientific. Ah, there we go, lads. Sorry, I should have figured that one from the beginning. Divided by parentheses 0.3928 minus 0.001095. Yep. And so, as you guys can see, let me see. It is 0.252, I believe is what it came across as. Yes. So 0.252. Did anybody else do that on their calculator and get that? Okay, so Tanner did. So 0.25. So I'll just call it 0.253. Let's just call it 0.253. So 0.253. So our x1 is equal to 0.253. That right here is our first thing that we need to find. So to find anything else, we have to have that value right here, which is 0.253. Now, really quickly, now we need to find the next one, which is internal energy 1. So let's hold on to 0.253. So I'm going to erase all of this. I hope you guys are okay with that. It's on the video. You guys will be able to find it later. So we found our quality of 0.253. Now, this next equation is going to look familiar, by the way, because it's the exact same equation as the one we just wrote, except we solved for quality. So U1 is equal to. So this is, by the way, so that quality equation I just wrote, that is like quality is equal to V1 minus VF over VG minus VF. That equation is the same one that I'm about to write, except that we solved for quality in the previous equation. This equation is the one for solving for internal energy. They're the exact same equation, though, just manipulated around. So U1 is equal to UF plus X1 times UG minus UF. So if you would look at this equation, this is the exact same equation. If you subtract over UF, you'd get U1 minus UF. And then if you divide UG minus UF over, you would solve for quality, right? These are the exact same equation. They're just written differently, right? And these will all be provided on an equation sheet. You do not have to worry about knowing these, right? But I would get used to them. So if we plug in all of these values to find our U1 and you take our quality and plug it into here, we will find an answer. So really quickly, let me go ahead and pull this back up. So go over to 150. And let's go to internal energy, which is this category right here. And our 150 are these two values. So U sub F is 631.68. U sub G is 2559.5. So hopefully you guys will 631. Let's go ahead and do that. So let's write that out. So we'll do 631.68, I think is what it said. Yep, 0.68. Plus 0.253 times the difference between that, which I'm going to write just 2559. Because we can, it's just a matter of looking at the tables, right? It's not, super important right now. But I just wanted to show you how we get this. And if anyone has done this one out yet, maybe Tanner has, if we're ever so lucky. But if not, I will go ahead and just do it. So 0.68 plus 0.253 times parenthesis 2559. So you would get 1100 and looks like 1119. Is that what anybody got? If you've done this, okay. So 1119. So let me go ahead and type that in. So 1119 thereabouts, right? 1119. And remember, this is in kilojoules per kilogram because it's an internal energy value. Quality has no units, and once again, the other ones were in meters cubed per kilogram, which is specific volume. So that is our second answer right there. Okay? So we have found quality one and internal energy one. And like I said, this is the exact same process for any variable you need to find under the saturation curve. They are all the same, just this process once again. But the last one here, though, is to find the pressure. So this is a tricky one. It's not so tricky, but it is funny. It would be interesting to see if who's been paying attention. So what is the pressure here? Anybody want to take a guess? Let me pull this back up. So we know the temperature is 150, right? We found an internal energy value in here. We have our 0.1 meters cubed per kilogram inside of here, right? We know it has a quality of 0.253. So what does that quality of 0.253 mean, right? So let's pull up this chart again. This will be the last thing we do before we leave. So remember, we know that we're in here, right? We are 25% this way, right? 25% vapor. So we're around here, right? Okay? So, can anybody tell me what you think the pressure is? I can't see the chart, the chat. I'll pull that back up. Okay. So, we are right about here. So, can anybody tell me what the pressure is? Okay, that is correct. So what is the pressure? 4.758, correct. That is the pressure. So essentially what that means is that at this temperature, so like I said, this is to see who was paying attention, because on the previous table we were given pressure and temperature was what was here. We had to reach that temperature for it to be for it to be able to reach saturation, to start boiling. This is the opposite. We're at this temperature and it has to be this pressure to start boiling. You see? So we are now, this is the pressure to start boiling, more or less. 4.758 bar was required to get us to start boiling at that temperature. So that was right. The answer is exactly right here. Is that 4.758. So those are our three answers. Our three answers are the ones that we just found. I'll pull them up one more time before we end the video. So it was 119 or 1,119 kilojoules per kilogram. Quality was 0.253, and our pressure one, how I would write it is P1 is equal to P sat, so the saturation pressure at 150 degrees C, which is equal to 758 or something like that. Bar. Sorry, a lot of units. Bar. So essentially the pressure one that we are looking for is equal to the saturation pressure at 150 degrees Celsius, which is 4.758 bar. That's how I usually write it. But let's put it this way, if you wrote it like this, but let's say you wrote the answer wrong. So for example, this will be the last word. If you wrote it like this, P1 is equal to P sat at 150 degrees C, and then let's say, for example, you accidentally pulled up the one under it, like 6.178, because you read down the table, because this does happen, right? There's a lot of lines, you read down the table wrong. You will get credit for this question, because you knew what you were doing, right? You did know where it was at. You just read down the line wrong. So you would get full credit for that. I am not. If you read down the line, that's okay. You just messed up, and that's a very easy mistake to fix. And so next time when we come back in here, we'll do more on this, because this is a very important subject, and we'll do more examples. I might have you guys do them, where I give you some questions on the screen, and you guys type in your answers into the chat, or you send them to me directly, and I'll just give you like 10 minutes on the clock to do like 3 of them, right? So next time, come in with the tables and come in prepared to do these questions, because it is very important that we know how to do this, okay? So I'm going to go ahead and end it, and